If you take a bare electrical conductor and bury it directly in the ground, it will fail almost instantly. The downward pressure of rocky, shifting soil is enough to deform the copper and crush the internal electrical pathways. Power cables are deployed into highly hostile environments. They have to survive the heavy, static load of underground soil, the constant saturation of wet trenches, and the extreme vertical suspension of primary coal mine shafts. On their own, the conductive core and its immediate layer of insulation have zero mechanical defense against these external physical forces. The operational lifespan of a power cable actually depends on a sequential defensive architecture. It requires an inner mechanical backbone to hold its shape, wrapped inside an outer environmental barrier to keep the elements out. The first line of defense is the cable armor. This is a robust structural layer designed specifically to absorb crushing forces, blunt impacts, and the extreme tensile stress of being pulled through underground conduits. The second line of defense is the outer sheath. This exterior jacket completely encapsulates the underlying layers, repelling moisture, soil chemicals, and radiation. Manufacturing these layers forces engineers to constantly weigh competing physical properties. They have to balance the high tensile strength needed to survive the Earth against the risk of the cable destroying itself through self-induced electromagnetic heat. Designing a globally compliant distribution cable requires looking past the conductor itself. The exact material trade-offs made in the outer layers are the only things keeping that internal copper alive. For standard multi-core configurations, the undisputed industry standard for mechanical protection is galvanized steel round wire, or SWA. Steel is selected because of its exceptionally high tensile strength. When a heavy-duty cable is subjected to direct burial or dragged through heavy industrial installations, the steel armor takes the physical strain. But certain environments push steel to its limits. In deep coal mines, the incoming supply cables have to drop straight down primary vertical pit shafts. That massive vertical drop requires a heavily reinforced armor design so the cable doesn't tear itself apart under its own weight. The solution to this extreme vertical stress is double wire armor, or DWA, making vertical cables entirely self-supporting. DWA consists of two dense layers of steel wires separated by a protective tape. The critical engineering detail is that the two layers of steel are applied with opposite directions of lay. Historically, engineers applied this double-layered protection to all the cables in the mine, including the horizontal runs along the roadways. But the counter-rotational steel layers created severe rigidity issues. That rigidity caused an immediate logistical failure. The mining crews physically could not coil the stiff, double-armored horizontal cables to fit them into the narrow lift shafts for transport. Today, manufacturers have adopted an engineered compromise. They reserve WA strictly for the vertical suspension drops and revert to single-layer SWA for fixed horizontal tunnels to maintain the flexibility needed for installation. Mechanical armoring forces a specific choice. Engineers trade maximum tensile support against the practical limits of how much the cable can bend during deployment. There is one configuration where steel is strictly banned. You cannot use magnetic steel armor on single-core cables carrying alternating current. To understand why, imagine an engineer wraps a single-core AC cable in high-tensile galvanized steel wire. As alternating current flows through that single central core, it naturally generates a powerful, continuously fluctuating magnetic field. Because the magnetic steel armor catches those radiating field lines, it acts as a secondary circuit. This induces heavy eddy currents, localized loops of electrical current circulating directly within the steel layer. These circulating currents generate massive electrical losses, immediately converted into severe heat. This creates a rapid thermal runaway effect. The heat bakes the internal insulation until it degrades completely, causing a total catastrophic failure. To break this induction cycle, single-core cables require an entirely different material approach. They must utilize non-magnetic armor to allow the magnetic fields to pass through without generating secondary currents. For these specific configurations, the replacement standard is aluminum wire armor, or AWA. Aluminum has a much lower tensile strength than steel, but engineers deliberately accept a weaker mechanical shell to ensure the cable actually survives its own electromagnetic forces. This drop in physical strength rarely causes structural issues in the field. Single-core cables are primarily deployed as short interconnectors, rather than being dragged through long, deep direct burial trenches. When designing high-voltage single-core transmission lines, the laws of electromagnetic induction dictate the architecture, overriding the need for maximum mechanical strength. Outside of the armor sits the final layer of the architecture. The outer sheath is an environmental barrier that entirely encapsulates the internal mechanics. Its primary function is defense against the elements. It repels moisture, soil chemicals, and physical abrasion that would otherwise rust the metal armor. Manufacturers typically choose between two standard polymers. Polyvinyl chloride, or PVC, provides cost-effectiveness and flexibility during the extrusion process. Polyethylene, or PE, is specified for harsher outdoor environments because it offers superior moisture blocking. But water and soil are not the only threats. For cables stored or deployed above ground, the most pervasive environmental danger is prolonged exposure to ultraviolet or UV radiation from the sun. The solution is chemical. Manufacturers deliberately color these outer sheets predominantly black by mixing carbon black directly into the polymer matrix. When incoming ultraviolet radiation strikes the dark polymer surface, those microscopic carbon black particles absorb the destructive energy and scatter it harmlessly. The outer jacket of a power cable is a chemically tailored compound built to endure decades of relentless elemental exposure. The last environmental constraint an engineer has to solve is thermal degradation, specifically how the sheath behaves during an active fire inside an enclosed space or a transit tunnel. Standard PVC sheaths effectively repel water and UV light, but they create a secondary hazard when burned. They emit dense, toxic, vision-obscuring smoke. To counter this, modern safety protocols mandate the use of low-smoke, zero-halogen, or LSCHCH compounds. These engineered plastics resist the spread of fire and eliminate the toxic off-gassing that traps people in enclosed spaces. None of these material choices are arbitrary. Every component we have discussed is legally dictated by a rigid matrix of manufacturing standards. In India, the Bureau of Indian Standards enforces these rules. Core insulation dimensions fall under IS 7098 and heavy-duty PVC under IS 1554. Steel armor galvanization is dictated by IS 3975 and outer sheath thermal stability by IS 5831. Globally, these codes map directly to IEC 60502, establishing exact tolerances for international compliance. Across Europe, the Middle East, and parts of Asia, engineers rely heavily on British standards, referencing BS 5467 for general thermosetting cables and BS 6724 specifically for LSCHCH compliance. Adherence to these specific alphanumeric codes is the only way a manufacturer can legally guarantee that their cable will physically and chemically survive its deployment. Look closely at a fully constructed power cable. The reliability of the electrical grid is manufactured sequentially, layer by layer. We balance the extreme tensile strength of counter-rotational double-wire armor against the necessary physical flexibility of a single-layer wrap. We substitute the immense durability of steel for softer, non-magnetic aluminum to ensure our single-core cables don't melt from their own induced eddy currents. And we mix exact ratios of carbon black and zero-halogen polymers to defend the internal mechanics from decades of solar radiation and the risks of tunnel fires. A modern power cable is an exercise in engineered compromise. It is a precise translation of physical science, chemical limitations, and strict compliance codes into the resilient infrastructure required to power the globe.